Tonight, the skies over the United States are shifting into something much bigger than an ordinary storm pattern. A bomb cyclone warning is raising concern, and weather across the country could change dramatically for the next 2 weeks, bringing powerful winds, heavy rain, snow, and dangerous coastal conditions. In this video, the full story unfolds, from the forces building high in the atmosphere to the real impacts on the ground. Before diving in, please like this video, subscribe to the channel and turn on notifications so more people can find these weather updates. A broad view settles over the United States as the atmosphere arranges itself into a pattern that spans an entire continent. The land stretches from the Pacific Ocean to the Atlantic Ocean, and above it, the air moves in large, slow arcs that shape weather across many days. This wide perspective does not focus on a single storm or a single city. It holds the entire region at once, observing how temperature and moisture shift across plains, mountains, forests, and coastlines. The pattern develops gradually, guided by forces that operate far above the ground and far beyond any one place. Across the western edge, air flows inland from the Pacific, carrying moisture that has gathered over open water. Along the eastern boundary, the Atlantic breathes its own influence into the atmosphere, sometimes adding warmth, sometimes feeding clouds that drift inland. Between these edges lies a complex interior where air masses meet, mix, and move. Some of this air is cold and dry, descending from higher latitudes. Some is warm and humid, rising from lower latitudes. Their boundaries shift from day to day, forming invisible lines that guide where clouds gather and where clear skies persist. The pattern is not fixed. It evolves over a span of roughly 2 weeks, shaped by the steady progression of atmospheric waves. These waves are not visible in the same way as ocean waves, yet they carry energy and motion across the sky. They influence where high pressure settles and where low pressure forms. High pressure regions tend to bring calmer conditions, with air that sinks and spreads outward near the surface. Low pressure regions, by contrast, draw air inward and upward, encouraging cloud formation and precipitation. The balance between these regions determines whether a place experiences dry air, steady rain, or changing conditions. Temperature spreads unevenly across the country. In some areas, cooler air lingers, held in place by the slow movement of larger atmospheric structures. In other regions, warmer air advances, sometimes reaching farther north than usual for the season. These shifts are not abrupt but gradual, like a slow tide of warmth and coolness that ebbs and flows. Over several days, one region may transition from mild conditions to colder air, while another experiences the opposite change. The pattern does not act uniformly, and this unevenness is part of its nature. Moisture follows similar paths. In certain regions, air carries enough water vapor to support cloud formation and precipitation. In others, the air remains relatively dry, allowing clearer skies and greater temperature variation between day and night. When moist air encounters lifting forces, such as rising motion within the atmosphere, clouds thicken and may produce rain or snow. When air sinks, clouds tend to dissipate, leaving clearer conditions behind. These processes occur continuously, shaping the appearance of the sky from one day to the next. The timescale of 2 weeks allows the pattern to show both persistence and change. Some features remain in place for several days, creating stretches of similar weather. Other features shift more quickly, bringing transitions that may feel abrupt at the surface. Meteorologists describe these changes using probability rather than certainty. Observations indicate that certain regions are more likely to experience above-average temperatures or increased precipitation, while others may lean toward cooler or drier conditions. It remains uncertain exactly how each local area will experience these trends, because small variations in the atmosphere can lead to different outcomes. The large-scale pattern also reflects the season. As the year progresses, the contrast between cold and warm air changes, influencing how strongly the atmosphere can generate storms. During periods when temperature differences are pronounced, the atmosphere holds more energy for movement and transformation. When these differences weaken, the pattern may appear calmer, with fewer dramatic shifts. In this particular span, the balance suggests a period of active change, where transitions in temperature and precipitation occur across wide regions. Over the central plains, the open landscape allows air to move freely. Here, changes in wind direction can quickly alter temperature and moisture. A flow from the north may bring cooler, drier air, while a flow from the south can introduce warmth and humidity. These shifts contribute to the overall pattern, feeding into larger systems that extend beyond the plains themselves. Mountains to the west and east further shape the flow, guiding air upward or blocking its path. Adding another layer of complexity, the pattern extends upward through the atmosphere. Even though this section remains focused on the broad surface expression, what appears at ground level reflects deeper processes that unfold above. The arrangement of high and low pressure at the surface connects to motions higher in the sky, where air currents move with greater speed and influence. Although these upper layers are not yet examined in detail, their presence is felt in the way the surface pattern evolves. Across the southern regions, warmer air often holds more moisture, creating conditions that can support cloud development along the northern edge. Cooler air tends to be drier, though it can still produce clouds when lifted. The meeting of these air masses does not occur in a single place but shifts gradually across the country. These shifting boundaries define where precipitation may become more frequent and where skies may clear. Throughout this period, the atmosphere maintains a delicate balance between stability and change. Some days bring steady conditions, where the pattern holds firm. Other days introduce new influences, altering the distribution of temperature and moisture. This interplay continues over the entire 2-week span, shaping the experience of weather across the United States without settling into a single, unchanging state. The broad pattern remains the outermost layer of understanding. It does not yet reveal the details of individual storms or the mechanisms that drive rapid changes. Instead, it provides a foundation, showing how the atmosphere organizes itself on a continental scale. From this wide perspective, the stage is set for more focused processes that develop within it, each guided by the same fundamental forces of air movement, temperature contrast, and moisture flow. Far from the inland towns and highways of the United States, the outer environment of this weather pattern takes shape over open water. The ocean lies broad and patient beneath the atmosphere, storing heat, releasing moisture, and helping to sustain the contrast that supports strong cyclones. Along the Pacific margin and along the Atlantic margin, conditions over the sea differ from those over land in ways that matter deeply to the development of a powerful mid-latitude storm. The water changes temperature more slowly than the ground. It holds warmth across long spans of time, even when colder air begins to move above it. This slow response gives the lower atmosphere a steady source of energy and moisture. Near the ocean surface, air absorbs water vapor through evaporation. This process is quiet and constant. Wind moving across the sea enhances it by carrying moist air away and allowing drier air to take its place. When the air above is cold and the water below is relatively warmer, The exchange becomes stronger. Heat moves upward from the ocean into the atmosphere. Moisture rises with it. The result is an environment that can help organize cloud bands, deepen low pressure, and increase instability in the lower layers of the air. The sea does not create the cyclone by itself, yet it helps prepare the broad outer setting in which a cyclone can strengthen. The Pacific Ocean often presents long reaches of open water where storms travel eastward within the belt of westerly winds. These storms form and evolve over distances much greater than those visible from any shoreline. Over this open expanse, the atmosphere can gather structure gradually. Air masses from different origins move over the sea and begin to interact. One air mass may be cool and dry, carried from higher latitudes. Another may be milder and more humid, associated with lower latitudes or with air that has lingered above warmer water. Where these air masses begin to press against one another, the ocean below continues feeding moisture into the lower atmosphere, making the contrast more active. The Atlantic margin offers a related but distinct setting. Along parts of the western Atlantic, relatively warm currents help maintain surface water temperatures that differ sharply from the air above during active weather periods. If colder continental air moves seaward over these waters, the contrast can become pronounced. Heat and moisture rise from the sea into the lower atmosphere, thickening the marine layer and encouraging stronger vertical mixing. This does not guarantee rapid storm development. Yet observations show that such contrast often supports intensification when the larger atmospheric structure is already favourable. The storm responds not to one cause alone, but to a combination of ingredients working together. The ocean surface is never uniform. Temperature varies from place to place. Currents transport warm water and cold water along shifting paths. Waves roughen the surface and increase the contact between air and sea. Areas of colder, upwelled water may lie near regions of warmer flow. These variations influence the rate at which heat and moisture enter the atmosphere. A cyclone moving over or near these waters encounters an uneven lower boundary, one that can strengthen some parts of the cloud field more than others. Even before pressure falls sharply, the broad marine environment begins shaping the storm's outer character. Clouds over the sea often reveal these processes before the land feels their full effects. Long streamers of marine clouds can form where cold air moves over warmer water. Wide shield-like layers of cloud can spread outward from organizing low pressure. In satellite imagery, these structures show curvature and expansion, yet from the surface they remain only layers of grey, white, and shadow over water. Within them, rising air cools and condenses, latent heat. The energy released when water vapor becomes liquid droplets adds to the storm environment. This release of heat does not act alone, but it contributes to the growth and maintenance of cloud systems that wrap around the broader circulation. The ocean also affects pressure indirectly through its influence on temperature. Pressure differences at the surface arise in part from the density of air, and density depends on temperature and moisture content. Air that is warmed from below becomes more buoyant. Air enriched with moisture behaves differently from dry air, especially when it begins to rise and condense over large marine areas. These small thermodynamic changes accumulate into meaningful differences in the atmosphere's structure. The sea becomes not merely a background, but an active lower boundary that helps define how air behaves in the storm's outer zone. Wind over the ocean reveals another aspect of this region, because the sea surface has less friction than forests, cities, or broken land. Air can move across it more smoothly and often more quickly. This allows broad wind fields to develop with fewer interruptions. Moist air can be transported over long distances. bands of stronger flow can organize around an offshore disturbance, feeding it with momentum and moisture. At the same time, the sea state responds. Waves grow with fetch. The distance over which wind blows across water. Swells spread outward from stronger wind zones. These ocean responses remain part of the outer region because they reflect the first large interaction between storm and surface. Yet uncertainty always remains. A favourable ocean environment does not ensure that a cyclone will become exceptionally intense. The atmosphere above must also be arranged in a supportive way. If the upper flow is poorly aligned, the moisture and heat from the sea may produce only clouds and moderate precipitation rather than rapid deepening. If the temperature contrasts are weaker than expected, the exchange between air and sea may be less effective. Forecast models estimate these relationships using observations from satellites, buoys, ships, and coastal stations, but exact outcomes remain uncertain because the atmosphere and ocean interact continuously and unevenly across large distances. The sea therefore serves as the broad outer cradle of the system. It offers moisture without interruption. It releases stored heat into colder passing air. It sustains sharp contrasts where water and air differ strongly in temperature. It allows wind to travel with fewer obstacles. It shapes cloud formation before the storm reaches land. In this region, the bomb cyclone warning still exists as possibility rather than detail. The ocean provides the expansive setting in which that possibility grows clearer. It is the first physical layer that gathers the raw materials of intensification, surrounding the storm with water vapor, temperature contrast, and long uninterrupted flow. Nothing here depends on a single dramatic moment. The changes are gradual, cumulative, and physical. The sea remains beneath the air, steady and immense, while the atmosphere above it organizes into larger motion. Along the ocean edge of the United States, the outer environment of a powerful weather shift is prepared through contact between water and air, through the quiet exchange of heat and moisture, and through the persistence of broad marine conditions that support a storm long before the storm is fully understood at the ground. Above the ocean surface and above the shifting pressure fields over land, the atmosphere continues upward into a faster and more organized realm. In this broad upper region, the air flows in long rivers that circle the hemisphere. These currents are not seen directly from the ground, yet their influence is present in the movement of clouds, in the direction of storms, and in the changing distribution of warm and cold air across the United States. This layer forms the steering region of the weather pattern. It guides where storms travel, where air rises, and where sinking motion allows calmer weather to spread. In a period marked by warnings of rapid cyclone development and extended change, the upper flow becomes one of the most important regions to observe. The most influential feature in this region is the jet stream. A jet stream is a narrow band of strong wind high in the atmosphere, usually found near the boundary between colder polar air and warmer air to the south. It does not follow a straight path. It bends in wide curves, dipping southward in some places and arching northward in others. These bends matter because they shape the larger pattern beneath them. Where the jet stream curves deeply toward the south, colder air is often able to move farther across the country. Where it arches northward, milder air tends to spread. The flow above becomes a guide for the temperature changes felt below. Within the jet stream, wind speed is not the same everywhere. Some stretches contain especially strong currents, and these faster segments can encourage motion in the layers beneath them. When air accelerates and changes direction in the upper atmosphere, it can create regions where mass is removed more efficiently from above. This removal allows surface pressure to fall more readily below. The process is subtle from a human viewpoint, yet it is central to storm development. A cyclone near the surface becomes more likely to strengthen when the upper winds are arranged in a way that supports rising motion and pressure falls. The steering region therefore does more than push storms along. It helps determine whether they organize slowly or deepen quickly. The upper pattern also contains large waves. These are often described as troughs and ridges. A trough is an elongated region of lower pressure or colder air aloft, usually associated with a southward dip in the flow. A ridge is an elongated region of higher pressure or warmer air aloft, usually marked by a northward bulge. Together, troughs and ridges create the slow undulation of the atmosphere across the continent. A trough often favours rising motion downstream, meaning ahead of it in the direction of the flow. A ridge often supports broader sinking motion and more settled conditions. During an active 2-week period, these waves may move across the country one after another, or one of them may linger, causing a persistent pattern of cooler or warmer conditions. When a trough sharpens, the air within it becomes more dynamic. Cold air aloft increases the contrast with warmer air below, and the curvature of the flow can enhance lift in certain areas. This does not automatically produce a bomb cyclone, but it provides one of the upper ingredients that can support rapid deepening near the surface. The warning of a major change over the United States often begins here, in the shape of the upper air wave pattern, before the full consequences appear in local forecasts. The atmosphere high above arranges the lanes in which storms travel and the broader zones where rising motion becomes more likely. The steering region also determines how long a weather pattern may persist. If the upper flow moves steadily from west to east, storms and temperature changes may pass across the country in an orderly sequence. If the flow slows and becomes more amplified, with larger north-south bends, conditions can linger. A ridge may hold warmth over one region for several days. A trough may keep cool, unsettled weather in place over another. In some cases, the flow becomes blocked, meaning the large waves move only slowly. This can extend a weather regime well beyond a few days and help explain why change may last for roughly 2 weeks rather than passing quickly. Cloud patterns often reveal the upper steering flow. Long bands of high cloud stream along the jet. Curved shields of cloud mark the areas where air is rising ahead of an upper trough. Clearer expanses can develop beneath regions of sinking motion. Yet the upper atmosphere is not simply a place of clouds. It is a place of pressure surfaces, temperature gradients, and wind relationships that act across great distances. A disturbance entering the Pacific may be shaped by one part of the jet stream and then later influence the plains and eastern states as it moves through the broader current. In this way, the upper region connects distant places within a single moving pattern. Forecasting this region relies on a wide network of observations. Weather balloons rise through the atmosphere and measure temperature, humidity, pressure, and wind. Aircraft provide additional data along major routes. Satellites infer motion from cloud drift and observe thermal structure over land and sea. These measurements feed numerical models that simulate how the upper pattern may evolve through time. Even with these tools, uncertainty remains. Small differences in the position of a trough or the strength of a jet streak can change where the most intense surface development occurs. A storm may deepen closer to one coast than expected, or the sharpest temperature divide may set up farther inland. The broad pattern can be anticipated with more confidence than the exact placement of each effect. In this steering region, the atmosphere is still operating on a wide scale. It has not yet narrowed into the low-pressure center itself. It has not yet defined the fronts or the wind field at the ground. Instead, it shapes the path toward those inner details. It arranges motion over the continent, places energy where storms can use it, and determines how warm and cold air are distributed across time and space. The United States below becomes the visible stage, but the direction of the play is set high overhead. The upper flow remains calm in appearance when imagined from far away. It forms no solid boundary and offers no fixed wall. It is air in motion, guided by the rotation of Earth, by the contrast between equator and pole, and by the continual rebalancing of temperature across the hemisphere. Yet within this seemingly smooth movement lies the architecture of an active weather period. The jet stream bends, speeds, and slows. Troughs deepen and ridges build. Areas of lift and sinking shift from region to region. Through these changes, the broad atmospheric steering pattern governs how a bomb cyclone may be guided, supported, or restrained during the days ahead. Within the broad steering pattern high above the continent, one region draws inward toward a more focused process. The air no longer appears only as wide waves and guiding currents. It begins to organize around a deepening low-pressure system, and here the meaning of a bomb cyclone becomes clear. The phrase refers to bombogenesis, a term used in meteorology for very rapid intensification of an extratropical cyclone. An extratropical cyclone is a low-pressure system that forms outside the tropics and gains strength from contrasts in temperature rather than from warm ocean water alone. In common discussion, the expression bomb cyclone may sound dramatic, yet in science it has a specific meaning. It describes the speed at which the pressure falls, not a special category of storm beyond the ordinary laws of atmospheric motion. At the center of this process is atmospheric pressure, the weight of the air above a given place. When pressure decreases at the surface, the surrounding air begins to move inward more strongly. This inward flow does not travel in a straight line to the center because Earth rotates. The rotation causes moving air to curve, producing the broad spiral circulation associated with the cyclone. As the pressure falls more quickly, the circulation usually strengthens, and the gradients around the storm become sharper. But the drop in pressure is not the cause by itself. It is a sign that the entire system is reorganizing in a way that favors rising air, stronger wind fields, and greater structure. Bombogenesis occurs when several supportive elements align. The low-pressure system must already exist or be forming. Above it, the upper atmosphere must be arranged so that air is efficiently removed from the column. Around it, strong temperature contrasts provide energy through baroclinicity, a term for the presence of strong horizontal differences in temperature. Near it, moisture and latent heat release may help maintain deep cloud formation and upward motion. None of these ingredients alone is enough. Together, they can allow central pressure to fall at a rate that meets the accepted threshold for rapid deepening. This threshold depends on latitude, because the effect of Earth's rotation varies from place to place. The underlying concept remains simple. The storm strengthens unusually fast for its region. As the low deepens, the air at the center rises more vigorously. Rising air cools, and its water vapor condenses into clouds and precipitation. The condensation releases heat, which can further influence the structure of the storm. This added heat does not replace the main role of temperature contrast across the system, but it can intensify cloud bands and support stronger ascent. The cyclone becomes a more organized engine of movement. Air enters at low levels, rises in preferred regions, and spreads outward aloft. The pressure continues to fall as the mass balance of the atmosphere shifts. The storm is not exploding in a literal sense. It is deepening through fluid dynamics, thermodynamics, and the persistent action of large-scale atmospheric flow. A rapidly deepening cyclone often develops a more distinct center. On weather maps, isobars, the lines of equal pressure begin to tighten and curve more sharply around the low. Satellite images may show cloud patterns wrapping inward, suggesting a growing circulation. At the surface, the effects are not always immediate in every location. Some places may first notice thickening clouds, others may experience a strengthening breeze or a gradual turn in wind direction. The full impact depends on where a region lies relative to the centre and to the fronts that extend from it. In the deepening phase, the most important change remains the internal acceleration of the system itself. This process can occur over the ocean or after a storm begins to affect the coast. Over water, the pressure may fall while few people directly observe it, detected mainly by buoys, ships, aircraft, and satellites. Near land, the deepening becomes more tangible as wind increases, clouds thicken, and precipitation expands. Yet the physical process remains the same. The storm is drawing energy from the contrast between different air masses, while upper-level support encourages stronger rising motion. In that sense, bombogenesis is not an isolated event but a moment of exceptional efficiency within the ordinary life cycle of a mid-latitude cyclone. Not every strong storm undergoes bombogenesis. Some storms become powerful but intensify gradually. Others form with promising ingredients but fail to deepen rapidly because one key element is missing or misplaced. The upper-level support may be too weak. The temperature gradients may be less pronounced than forecast. Dry air may intrude into important regions of ascent. The track may shift in a way that reduces interaction with the strongest contrasts. Because of these possibilities, meteorologists treat forecasts of rapid deepening with care. Models can identify favourable conditions, but exact rates of pressure fall remain sensitive to small changes in structure and timing. The term warning becomes meaningful here, though still in a scientific and measured way. A bomb cyclone warning is not a single official national product, with one universal threshold for public action in every context. Rather, it reflects the recognition that rapidly deepening storm may produce substantial impacts through wind, heavy precipitation, coastal hazards, and sharp temperature transitions. The deepening itself is a physical sign that the system may become more dangerous if it tracks near populated areas. The danger arises from the weather produced by the storm, not from the terminology used to describe it. This inner process also reveals a difference between public language and scientific precision. Public discussion often treats the phrase as if it names a rare object, almost separate from other storms. Scientific understanding is quieter and more exact. The storm remains an extratropical cyclone. It deepens because the atmosphere above and around it becomes especially favourable for pressure falls. The event may be intense, but it still follows known physical principles. Cold and warm air remain arranged across fronts. Upper winds continue to support rising motion. Moisture condenses, releases heat, and thickens clouds. The low centre tightens and strengthens. The cyclone becomes more efficient at reorganizing the surrounding atmosphere. From this region inward, the storm is no longer only part of a continental pattern or a marine environment or an upper air steering flow. It has acquired a core process of its own. Pressure falls rapidly. The circulation becomes more coherent. The system gathers strength through alignment of upper support, thermal contrast, and moisture. What begins as a broad possibility now becomes a defined act of intensification. In this stage, the storm changes from a feature guided by the pattern to a force that can begin shaping conditions over a wide area through its own rapidly deepening centre. Around the deepening low-pressure centre, the atmosphere arranges itself into a visible shape at the surface. This is the region of pressure structure, where the storm's inner organisation begins to appear as a pattern of lines, gradients, and directional flow. A cyclone that is strengthening rapidly does not affect the surrounding air in a random way. It draws the surface atmosphere into a coherent field. Pressure becomes lower near the center and higher farther outward. Between those zones, the change in pressure across distance, called the pressure gradient, becomes one of the main controls on wind. The closer the pressure lines lie to one another, the stronger this gradient tends to be. As the gradient tightens, the wind field gains force. On a weather map, this region is shown by isobars, lines connecting points of equal surface pressure. In a deepening cyclone, these lines curve around the center and often crowd together over a broad surrounding area. Their shape reveals not only where the storm is located, but how strongly it is influencing the lower atmosphere. A loosely organized low may show broad spacing between isobars and a weak circulation. A rapidly deepening low often shows a more compact center and a more pronounced gradient. The pressure structure becomes the surface signature of the storm's increasing intensity. Yet the wind does not move simply from high pressure to low pressure in a straight path. Earth's rotation turns the motion, and surface friction alters it further. The result is a spiraling inward flow that circles around the low while also moving gradually toward it, over open water where friction is relatively small. The wind can align more closely with the curved pressure pattern over land, where forests, buildings, hills, and surface roughness slow the air. The flow turns more inward. This difference matters because it influences where air converges, where it rises, and where the strongest gusts may reach the ground. The same pressure structure can produce somewhat different surface responses depending on terrain and surface type. As the pressure gradient sharpens, the storm's reach becomes more extensive. Wind increases not only near the center, but often across wide sectors surrounding it. The storm does not need to pass directly overhead to bring significant changes. A distant but strongly deepening low can generate powerful winds across plains, coasts, and mountain corridors simply because the pressure difference between regions becomes large. One area may lie on the warm side of the storm, another on the cold side. Yet both can experience strong flow if the isobars remain tightly packed. In this way, the pressure field acts as a broad mechanical framework for the weather that follows. The surface pattern also reveals how the storm relates to neighboring areas of high pressure. A cyclone does not deepen in isolation. Often a ridge or anticyclone stands nearby, creating a larger contrast across the region. When a strong high-pressure area sits west or north of a deepening low, the difference between their values can become substantial. Air responds to this contrast by accelerating between them. The strongest winds may therefore arise not only because the central pressure is low, but because the surrounding pattern amplifies the gradient. A moderately deep low paired with a very strong high can produce remarkable wind, while an even deeper low with weaker surroundings may create a less extensive wind field. The full pressure structure matters more than the center alone. This surface pattern changes with time. In the early stage of deepening, the isobars may still appear somewhat open and elongated. As the cyclone intensifies, they tighten and wrap more cleanly around the center. If the system begins to mature and then weaken, the pattern may broaden again. These changes reflect the storm's life cycle. During the most active phase, the pressure field becomes both more concentrated and more efficient at driving motion. That efficiency is felt as steady, strong wind, sudden gusts, and growing mechanical stress on trees, power lines, structures, and waves. Still, the pressure itself remains invisible. Only instruments record its exact value. Human experience comes through the moving air that pressure differences create. Barometers, whether at airports, weather stations, or ships. Register these changes as a falling pressure tendency. A rapid fall over several hours can signal that a storm is approaching or strengthening. This tendency is often as informative as the absolute value itself. A place may not record an extremely low pressure by historic standards, yet if the fall is swift and the surrounding gradient sharpens, the local effects can still become notable. Meteorologists therefore examine both central pressure and the distribution of pressure around the system. It is the structure of the whole field that determines the breadth and severity of the surface response. The shape of the land further modifies this region. Mountain ranges compress flow through passes and along slopes, enhancing wind in certain corridors. Broad plains allow air to accelerate over long distances with fewer interruptions. Coastal zones can experience changes in friction where land meets sea, altering wind direction and gust behavior. Urban environments add turbulence and local variation. The pressure field exists above all these surfaces, but the expression of that field at ground level becomes filtered through geography. A single synoptic scale pattern can therefore feel different from one region to another, even when the larger storm remains the same. Uncertainty persists here as well. Forecast models usually capture the existence of a deepening low and its general track several days in advance, but the exact arrangement of the tightest gradients can shift by enough distance to matter greatly for local impacts. A slight change in the storm path may place the strongest pressure difference over a coastal plain instead of inland hills, or over a mountain front instead of farther east. Such shifts alter wind potential, precipitation placement, and even how quickly temperatures change in a particular area. For this reason, the surface pressure pattern is monitored continuously as new observations arrive. In this region, the cyclone becomes legible in the simplest physical terms. Air has weight. That weight varies from place to place. Differences in that weight set air in motion. This storm intensifies because the atmosphere rearranges its mass, lowering pressure in the center and sharpening the gradient outward. The result is a surface field that gathers the surrounding air into broad circulation. Before the fronts are examined in detail, before the rain and snow bands are traced, the pressure structure already defines the storm's body. It is the map of force beneath the weather, the surface imprint of a rapidly deepening cyclone organizing the air across a large part of the United States. Extending outward from the deepening low-pressure center, the storm organizes itself through boundaries. These boundaries are called fronts, and they mark zones where air masses of different temperature and density meet. A front is not a wall and not a line that can be seen directly at the surface. It is a transition region, often broad in some places and sharper in others, where the atmosphere rearranges warm air, cool air, moisture, wind, and cloud. Around a mature or rapidly deepening extratropical cyclone, the frontal structure becomes one of the clearest signs that the storm is functioning as a complete system. The low-pressure center alone does not define the weather. The fronts extending from it distribute that weather into distinct regions. The cold front usually trails away from the low toward the south or southwest. Along this boundary, colder and denser air advances, pushing under warmer air ahead of it. Because the colder air is heavier, it tends to force the warmer air upward more abruptly. This lifting can produce a narrow but active band of clouds and precipitation. In some situations, showers or thunderstorms develop along the cold front if the air ahead of it contains enough moisture and instability. In other situations, the front passes with a more modest line of rain and a steady turn in the wind. The essential process remains the same. One air mass displaces another, and the atmosphere responds through rising motion, condensation, and change. The warm front typically extends eastward or northeastward from the low. Here the arrangement is different. Warmer air advances, but because it is lighter than the cooler air ahead of it, it slides upward more gradually over the denser surface layer. This produces a gentler slope through the atmosphere. Clouds often thicken in stages ahead of the front, beginning high and becoming lower and denser with time. Precipitation associated with a warm front is often broader and steadier than precipitation along a cold front, though the exact character depends on moisture, temperature structure, and the speed of the system. The frontal zone becomes a layered region of ascent rather than a sharply forced boundary alone. Together, the cold front and warm front define the warm sector of the cyclone. This is the region between them, where relatively warm and often more humid air occupies the lower atmosphere. The warm sector can feel unsettled even before the fronts themselves arrive. Winds strengthen, cloud cover varies, pressure may continue falling. The air may seem mild compared with surrounding regions, yet it remains part of the storm's broader circulation. The warm sector is not calm. It is the lower-level reservoir of air that the cyclone draws inward and then redistributes along its boundaries. Its presence helps the storm maintain thermal contrast, which remains central to the cyclone's strength. As the storm continues to develop, the frontal structure often begins to wrap around the low. The cold front usually moves faster than the warm front. Over time, this allows the colder air behind the cold front to catch up with the cooler air ahead of the warm front. When this occurs, the cyclone begins forming an occluded front. An occluded front is a boundary where the warm air near the center is lifted off the ground, leaving cooler or colder air at the surface on both sides. The low becomes more tightly wrapped, and the surface pattern grows more complex. The occlusion is not a separate storm but a later stage in the cyclone's structural evolution. It shows that the warm air that once fed directly into the center is being lifted and cut off near the ground. The region of the fronts is one of continual motion. Air converges toward the boundaries, rises, cools, and produces cloud. Temperature changes occur across relatively short horizontal distances. Winds often shift direction noticeably when a front passes. Pressure tendencies change as well. Ahead of a cold front, pressure may fall and winds may draw from warmer directions. Behind it, pressure often begins to rise and winds turn toward cooler flow. Ahead of a warm front, the sky may gradually fill with cloud, while temperatures near the surface can remain cool until the boundary passes. These changes are familiar in daily weather, yet around a deepening cyclone they become more organized and often more extensive. Not all fronts behave in the same way. A cold front moving through dry air may bring only a wind shift and a narrow line of cloud. A warm front in a moist and stable environment may produce long periods of light precipitation and low cloud. A front passing across mountains may weaken, break into segments, or reorganize as the terrain disrupts the lower flow. Along coastlines, the contrast between land and sea can alter the boundary further. The front remains a real atmospheric structure, but its local expression depends on the environment through which it moves. This is one reason forecasts must remain specific to region, rather than relying only on the broad label of the front itself. The frontal region also helps explain why a bomb cyclone can produce many kinds of weather at once. The same storm may generate steady rain north of the warm front, gusty mild air in the warm sector, heavy showers along the cold front, and mixed precipitation nearer the wrapped-up center. These are not separate events. They are different expressions of the same organized set of boundaries extending from the low. The fronts partition the atmosphere into zones, each with its own temperature structure, moisture content, and preferred type of ascent. Understanding the storm means understanding how these boundaries position one air mass relative to another. Meteorologists analyze fronts using surface observations, radar, satellites, and model fields of temperature and wind. Yet uncertainty remains because fronts are not perfectly sharp everywhere, and their exact placement can shift within a few hours. A slight displacement of a warm front can determine whether a town remains in cool, stable air or enters a milder, more humid sector. A modest change in the speed of a cold front can alter the timing of rain, the risk of thunderstorms, or the arrival of colder air. The fronts are physical boundaries, but they are living boundaries in a moving fluid, never entirely fixed. In this region, the cyclone shows how it arranges the lower atmosphere into order. The deepening low at the center provides the circulation, but the fronts provide the structure. They define where air rises abruptly and where it rises gradually. They shape the cloud fields, organize the precipitation, and set the stage for the changing conditions that follow. Around the core of the storm, the boundaries wrap outward and inward at once, tracing the lines along which the atmosphere sorts warm air from cold and turns a broad pressure system into a complete and active weather pattern. Within and along the frontal structure, the storm draws in moisture from its surroundings and channels it toward regions of rising motion. This inward flow of moisture is not random. It follows the pressure pattern and the wind field, moving along curved paths that spiral toward the low. As air travels, it carries water vapor that has evaporated from oceans, lakes, soil, and vegetation. In the outer regions, this vapor may remain invisible, mixed within clear air. As the air approaches the storm's active zones, especially near fronts and areas of lift, it begins to rise. Rising air cools, and as it cools, its capacity to hold water vapor decreases. The excess vapor condenses into tiny droplets, forming clouds. This process marks the transition from invisible moisture to visible weather. The supply of moisture is essential for sustaining cloud systems and precipitation. In a developing or rapidly deepening cyclone, the flow often organizes into corridors where moisture transport becomes especially efficient. These corridors can extend over long distances, linking warm, humid regions to the storm's core. Air from lower latitudes may be drawn poleward, bringing higher humidity into regions that were previously drier. This transport does not occur in a straight line. It follows the curved wind field around the low, often entering the system on its eastern or southeastern side, and then rising along the frontal boundaries. The result is a continuous feeding of moisture into the storm. As moist air ascends, condensation releases latent heat. This heat is energy that was stored when water evaporated at the surface, and is now returned to the atmosphere as vapor becomes liquid. The release of this heat warms the surrounding air slightly, making it more buoyant and helping to sustain upward motion. In this way, moisture does not only produce clouds and rain, it also contributes to the storm's internal energy balance. While the main driver of an extratropical cyclone remains the contrast between warm and cold air, latent heat release can enhance the intensity of certain regions within the system, especially where ascent is already strong. Cloud structures reveal the pathways of moisture. Broad, layered clouds often form ahead of a warm front, where moist air rises gradually over cooler air. Narrower, more active bands can develop along a cold front, where lifting is more abrupt. Near the center, where the system may be wrapping inward, clouds can form curved patterns that reflect the spiral flow. These structures are not static. They evolve as the moisture supply changes and as the fronts shift position. Some areas may experience persistent cloud cover and steady precipitation, while others may see breaks in the clouds as drier air intrudes. The vertical distribution of moisture also matters. Not all parts of the atmosphere contain the same amount of water vapor. In some cases, moist air is concentrated in the lower levels, while the air above remains relatively dry. When lifting occurs, the lower layers may produce clouds, but the development may be limited if the upper layers do not support continued ascent. In other cases, deep layers of moisture extend through much of the atmosphere, allowing clouds to grow vertically and precipitation to become more widespread or intense. These differences help explain why some regions within the same storm receive heavier precipitation than others. The interaction between moisture and temperature determines the type of precipitation that reaches the ground. In warmer sectors, condensation produces liquid droplets that may fall as rain. In colder regions, especially where the entire column of air is below freezing, ice crystals form and grow into snow. In intermediate cases, where a layer of warmer air exists above a colder surface layer, precipitation may melt and then refreeze, leading to sleet or freezing rain. These outcomes depend on the vertical temperature profile, but they all begin with the same basic process of moisture being lifted and condensed within the storm. Wind plays a central role in distributing moisture. Stronger winds can transport humid air more rapidly, feeding the storm's active regions and maintaining precipitation over time. At the same time, wind can also introduce drier air from other regions, especially on the western side of the cyclone or in areas where descending motion dominates. When drier air mixes into a cloud system, it can reduce cloud thickness and weaken precipitation. This balance between moist inflow and dry intrusion adds complexity to the storm's behavior. It means that precipitation patterns are not fixed, but can shift as the internal flow evolves. The ground below responds to this incoming moisture in different ways. Dry soil may initially absorb rainfall, while saturated ground can lead to runoff and accumulation. Snow-covered areas may experience additional snowfall or a transition to mixed precipitation if warmer air moves in. Rivers, streams, and urban drainage systems respond to the amount and duration of precipitation. These responses are part of the broader impact, but in this region, the focus remains on how moisture is delivered from the atmosphere to the surface. Uncertainty remains in the exact placement and intensity of moisture transport. Forecast models can identify the general corridors where humid air is likely to flow, but small shifts in wind direction or speed can alter where the heaviest precipitation occurs. A slight change in the position of a front can move a band of rain or snow from one region to another. The depth of moisture and the strength of lift can also vary, leading to differences in rainfall totals or snowfall amounts. Observations from satellites, radar, and surface stations help refine these forecasts as the storm develops, but variability persists. In this region, the storm structure becomes richer and more dynamic. The pressure field and frontal boundaries provide the framework, but moisture gives the storm its visible substance. Clouds thicken, precipitation forms, and latent heat subtly reinforces the system. Air continues to spiral inward, carrying water vapor from distant sources and releasing it as rain or snow. The cyclone is no longer only a pattern of pressure and wind. It becomes a moving system of water in different forms, cycling between vapor and liquid or ice, shaping the weather experienced across wide areas as it continues to evolve. At the heart of the cyclone's strength lies a contrast that is both simple and profound. The storm depends on the meeting of different air masses, and this meeting is defined above all by temperature. One side of the system contains colder, denser air, another holds warmer, lighter air. Between them lies a zone where the atmosphere changes sharply across distance. This thermal boundary is not merely a background feature. It is one of the main sources of energy for the storm. In an extratropical cyclone, the atmosphere is trying to reduce this imbalance, and the storm becomes one of the ways in which that adjustment takes place. Cold air and warm air do not mix instantly. They retain their identity over wide regions, especially if they arrive from different source areas. Air that has travelled from higher latitudes tends to be colder and often drier. Air that has come from lower latitudes or from warmer water tends to be milder and often more humid. When these air masses lie near one another, the atmosphere contains what meteorologists call a horizontal temperature gradient. This means that temperature changes noticeably from one place to another across the land and sea. The greater this contrast, the more potential the atmosphere has to generate organized motion. The reason lies in density. Colder air is denser, and therefore tends to remain lower in the atmosphere. Warmer air is less dense and more buoyant, so it tends to rise when it is forced or when the surrounding conditions allow. When a cyclone forms along a boundary between these air masses, it begins to draw them into a rotating pattern. Warm air is pulled poleward and inward on one side. Cold air is drawn equatorward and inward on the other. The storm is not simply sitting on top of a contrast. It is actively reshaping that contrast, wrapping the temperature zones around its center and using their difference to sustain motion. This process is called baroclinic development. The word can sound technical, but its meaning is direct. It refers to a state in which surfaces of equal pressure and surfaces of equal density are not aligned, allowing potential energy in the temperature contrast to be converted into wind and rising motion. In plain terms, the atmosphere contains energy because warm and cold air are arranged side by side rather than evenly distributed. The cyclone taps into that arrangement. As the warm air rises and the cold air undercuts or surrounds it, the storm intensifies its circulation and strengthens its internal structure. The thermal contrast is often strongest near the fronts, but it also extends more broadly through the storm. Ahead of the cold front, the air may be notably milder than the air behind it. North of the warm front, surface air may remain cool while warmer air rides above it. Around the wrapping center of the cyclone, these contrasts become curved and layered. The temperature field is no longer a simple straight boundary. It becomes part of the storm's spiral form. Yet even in this more complex shape, the basic engine remains the same. Different air masses remain in contact, and the atmosphere continues responding to that imbalance. A stronger temperature contrast generally supports a more vigorous storm, provided the other ingredients also align. If the air masses are sharply different and the upper atmosphere supports rising motion, the cyclone can intensify more efficiently. If the contrast is weak, the storm may still form, but it often has less energy available for rapid growth. This is why the season matters. During times of year when cold air still reaches southward while warmer air remains available to the south or over nearby water, the gradient can be especially favourable for a powerful mid-latitude system. The storm becomes, in effect, a moving boundary where seasonal differences are being redistributed. The contrast also influences the sky and the feel of the weather. On the warm side, the air may seem softer, more humid, and more active. On the cold side, it may feel sharper, drier, and more stable near the surface, though not always calmer. Clouds take different forms depending on which side of the contrast a place occupies and how the air is lifted. Precipitation type changes as temperature changes, but even before rain or snow begins, the storm's character is already shaped by where a location stands relative to the thermal divide. A place near the sharpest contrast often experiences the most rapid transitions in wind, cloud, and temperature. The atmosphere does not erase this gradient quickly. Instead, This cyclone converts part of it into motion. Warm air is lifted and transported, cold air advances and wraps inward. Over time, this can reduce the contrast near the centre, especially as occlusion develops and the warm air is lifted from the ground. But during the active phase of the storm, the gradient remains a source of structure and strength. It helps determine where ascent is strongest, where clouds deepen, and where the pressure may continue to fall. Without the thermal contrast, the cyclone would lose much of its ability to organize itself so effectively. Terrain can sharpen or soften these differences. Mountains may block colder air, allowing it to pool on one side while warmer air rides above it. Plains may permit warm and cold air to spread more freely, increasing the area over which they meet. Coastal regions may add the influence of ocean temperature, sometimes creating local contrasts that feed into the larger storm. Yet despite these regional modifications, the central truth remains unchanged. The cyclone thrives where temperature differences are preserved and drawn into circulation. Forecasting this thermal region involves careful attention to both horizontal and vertical structure. Surface observations reveal where the air is warmer or colder at the ground. Weather balloons show how the temperature changes with height. Numerical models estimate how the contrast will shift as the storm moves. Even with these tools, exact placement remains uncertain. A small shift in the boundary between air masses can determine whether a place receives cold rain, wet snow, or only cloud and wind. It can also alter where the storm strengthens most efficiently. The gradient is broad enough to define the storm, yet delicate enough that local effects depend on small details. In this region, the cyclone's power becomes understandable as a response to imbalance. The storm is not fueled by violence in any abstract sense. It is fueled by difference. Warm air and cold air meet across a continent and along the edges of the sea. They resist immediate blending. The atmosphere responds by generating motion, ascent, cloud, and circulation. The cyclone becomes a machine for redistributing heat, moving warmth poleward and cold equatorward, slowly reducing the contrast even as it depends on that contrast to remain strong. Here, in the temperature divide itself, the deepening storm reveals the physical reason it can change the weather of a nation for days at a time. As the storm continues to deepen and organize, the wind field spreads outward from the central pressure pattern into a broad moving envelope. This region is not limited to the tightest circle around the low. It extends across large areas, sometimes reaching far from the storm center itself. In a mature extratropical cyclone, the strongest winds are often arranged asymmetrically, shaped by the pressure gradient, the motion of the system, the structure of the fronts, and the changing influence of land and sea. The wind field becomes one of the storm's widest expressions, carrying its force across plains, coastlines, valleys, and ridges, sometimes long before the center passes nearest. Wind begins with differences in pressure. Air moves from areas of higher pressure toward areas of lower pressure, then curves because of Earth's rotation and adjusts because of friction near the ground. When the pressure gradient tightens around a deepening cyclone, the flow accelerates. Yet the strongest winds do not always sit directly beside the lower central pressure. They may be concentrated in particular sectors of the storm where the gradient is sharpest, where momentum from higher layers mixes downward, or where the storm's forward motion adds to the background flow. In this way, the wind field acquires a shape that is broader and more complex than a simple ring around the center. Over open plains, the wind can travel across long distances with relatively little interruption. Grassland, farmland, and gently rolling terrain do not slow the air as much as dense forests or cities. In these regions, broad areas of strong wind can develop and remain steady for many hours. The surface may respond through blowing dust, bending crops, swaying power lines, and rapid heat loss from exposed objects and bodies. Even without intense precipitation, the wind alone can define the storm's character. A place may experience only light rain or passing cloud and still feel the full power of the cyclone through persistent gusts and strong sustained flow. Along coastlines, the wind field interacts with the boundary between land and sea. Over water, lower friction allows the air to move more smoothly and often more quickly. As that air reaches land, turbulence increases and the flow adjusts. But strong gusts can still arrive with little warning. Where the coast faces directly into the stronger sector of the storm, wind may build waves, push water shoreward, and drive salt spray inland. Where the coastline bends or where hills rise near the shore, the local wind may strengthen further through channeling and compression. The broad wind field becomes filtered through local geography, producing variations that matter greatly to what people experience. In mountain regions, the storm's wind is modified again. Air passing over high terrain may accelerate through passes and gaps. On windward slopes, the flow rises and cools, often producing cloud and precipitation. On leeward slopes, descending air may become drier and in some cases stronger at the surface as momentum is transferred downward. Valleys can channel the wind into narrower paths, while ridgelines may receive the most exposed and persistent gusts. A single cyclone may therefore produce dramatically different wind effects over short distances in complex terrain, even while the larger wind field remains coherent on the weather map. The vertical structure of the atmosphere also influences this region. Strong winds often exist not only at the surface but in layers above it. If the lower atmosphere is well mixed, through daytime heating, precipitation-driven downdrafts, or turbulent mechanical stirring, some of that stronger wind aloft can be brought down to the ground. This is one reason gusts can become much stronger than the average sustained wind. The air does not move at one uniform speed from surface to sky. Instead, layers interact, and the ability of higher momentum air to mix downward helps determine the severity of surface gusts. In a rapidly deepening storm, this downward transport can make the wind field especially dangerous. The wind field also expands in response to the cyclone's scale. Some storms are compact, with the strongest winds confined closer to the centre. Others spread their gradients across a wider area, producing strong wind over several states at once. The warning of weather change over 2 weeks becomes meaningful here because successive systems, or one broad persistent pattern, can repeatedly expose regions to these wide wind envelopes. Trees that have already been weakened by saturated soil or prior gusts become more vulnerable. Infrastructure experiences cumulative stress. Travel becomes more difficult not only during the peak of one storm, but during an extended period of active atmospheric circulation. Wind affects temperature as well. Strong cold sector flow can intensify the sensation of chill by increasing the rate at which heat is removed from surfaces. In warmer sectors, strong southerly wind can rapidly transport mild, humid air northward, shifting local conditions within hours. The wind field is therefore not only a mechanical force, it is also a transport system, moving heat and moisture across broad distances. Through this transport, the cyclone reshapes the lower atmosphere while simultaneously producing the direct physical effects of gust and turbulence. The storm's motion adds another layer to the wind field. On the side where the rotational flow and the forward motion of the cyclone align, winds can become stronger. On the opposite side, where those motions oppose one another, the net surface wind may be somewhat less intense. This helps explain why one flank of a storm often feels harsher than another, even when both are close to the center. The circulation is not static. It is embedded in a moving system. And the movement alters the distribution of force across the wider region. Forecasting this region requires attention to scale and timing. Meteorologists must estimate not only the depth of the low and the shape of the pressure field, but also how the atmosphere near the ground will mix, how terrain will channel the flow, and where the strongest gradient will align. Small track changes can shift the corridor of strongest wind by enough distance to change the impact on cities, coastlines, or mountain communities. Observations from stations, buoys, radar, aircraft, and satellites refine the picture. Yet uncertainty remains because wind responds to both large-scale structure and fine local detail. In this region, the cyclone becomes felt as motion across the skin of the earth. Air that began as a response to pressure differences now sweeps outward in an organized envelope, touching many landscapes at once. It crosses open country with long, steady force. It curls along coasts, rises over mountains, and surges through valleys and streets. It carries cold and warmth, moisture and spray, dust and falling leaves. The wind field is the storm made tangible, not yet narrowed into rain bands or snow zones, but already spreading the cyclone's presence across a great distance through the constant moving weight of air. Beyond the broad wind envelope, the storm expresses itself through organized bands of rain. These bands are not spread evenly across the landscape. They form where moisture, lift, and atmospheric structure combine in narrow or wide corridors, sometimes curving around the cyclone, sometimes stretching ahead of its fronts, sometimes training repeatedly across the same ground. In this region, the storm's water reaches the surface in liquid form, and the quiet mechanics of condensation become visible as darkened soil, swelling streams, wet roads, dripping roofs, and long grey curtains moving across the land. Rain bands give the cyclone texture. They divide one place from another not by pressure alone, but by how much water falls, how long it lasts, and how persistently the clouds renew themselves overhead. A rain band begins with the scent. Air that is forced upward along a front or within a region of convergence cools until its water vapor condenses into cloud droplets. If this process continues through a deep enough layer, droplets grow large enough to fall. In some parts of the storm, the lifting is gentle and widespread, producing steady rain over many hours. In other parts, the lifting is stronger and more focused, producing narrower bands where rainfall becomes more intense. These differences matter. A broad area of light rain may soak the ground gradually, while a narrow, persistent band of heavier rain may overwhelm drainage systems and raise flood risk within a shorter time. The shape of the band depends on the internal structure of the storm. Ahead of a warm front, rain often spreads in layered sheets, extending far from the low-pressure center. Near the cold front, bands may become narrower and more active, sometimes broken into segments by changing instability and local wind structure. Closer to the center, curved bands can wrap around the circulation, marking the storm's spiral organization. These forms may seem different from one another, yet they are connected parts of a single water system. The cyclone lifts moist air in different ways at different locations, and the rain bands are the visible result of those differences. Some rain bands move steadily across the ground, allowing one place to experience rain for a limited period before the band passes. Others move more slowly or repeatedly across the same corridor. This repeated passage is often called training, because successive bands move along a similar track like carriages on a rail line. When training occurs, rainfall totals can increase rapidly, even if each individual band is not extreme. The ground has little time to dry or absorb fully between rounds. Small streams rise, low-lying roads collect water, urban surfaces, which shed water more quickly than natural ground, may flood sooner than nearby fields. The same storm can therefore produce ordinary rain in one county and localized flooding in the next, simply because the bands align differently. The intensity of rainfall within a band depends on the moisture content of the air, the depth of the cloud, and the strength and persistence of lift. Warm air can hold more water vapor than cold air, so rain bands in a milder and more humid sector often contain more available moisture. If the lifting remains strong and continuous, droplets continue growing and replenishing, and the rainfall rate can remain elevated. If drier air intrudes, the cloud may thin and the band weaken. If the lifting shifts, the band may move or dissolve. Rain bands are therefore living structures, changing in response to subtle adjustments within the storm. The ground response forms part of this region because rainfall only becomes impact when it meets the surface. Dry ground may first absorb much of the water. Saturated ground cannot. In agricultural land, compacted soils may shed more water than loose soils. In urban areas, pavement and roofs direct rain into drains, channels, and streets. In hilly terrain, water runs downslope quickly, gathering in creeks and low points, along rivers already running high. Additional rain may prolong or worsen flooding, even if the new rainfall is only moderate. The rain band itself remains an atmospheric structure, but its significance depends on the condition of the land beneath it. Visibility changes under these bands as well. A steady light rain may soften the landscape and obscure distant features. A heavier band can reduce visibility sharply, blurring roads, signs, and the edges of terrain. Travel becomes slower, not because the wind is necessarily strongest there, but because water is actively occupying the space between observer and world. Aircraft operations, road safety, and outdoor work all respond to this reduction in visibility. In this way, the rain band alters not only water levels but perception and movement. Temperature plays a quieter role here. In some rain bands, especially north of the warm front, evaporation of falling rain into drier air below can cool the lower atmosphere further, reinforcing a chilly surface layer. In warmer sectors, rain may fall through air mild enough that little cooling occurs, leaving conditions humid and heavy. The presence or absence of embedded convection also matters. Some bands remain stratiform, meaning layered and relatively uniform. Others contain taller elements where stronger upward motion briefly enhances rainfall. Yet even the more uniform bands can be important if they persist long enough. Forecasting rain bands is often more difficult than forecasting the storm as a whole. Meteorologists can identify the broad areas most likely to receive precipitation, but the exact placement of the heaviest corridors can shift with small changes in frontal position, low-level wind direction, or upper-level forcing. A difference of a few tens of kilometers may determine which drainage basin receives repeated rainfall and which remains only damp. Radar becomes especially important once the event begins, showing how the bands organize, intensify, weaken, or train over time. Forecast confidence may be high that rain will occur over a region, yet lower regarding where the most concentrated totals will finally fall. Within this region, the storm expresses itself not as an abstract map of pressure or temperature, but as repeated lines and arcs of falling water. The bands sweep across fields, towns, rivers, and roads, sometimes gentle, sometimes persistent, sometimes heavy enough to transform the surface within hours. They are shaped by the cyclone circulation, but they possess their own local rhythm, arriving, passing, and returning according to the hidden structure of lift and moisture overhead. Here the broad storm becomes a pattern of wet ground, running gutters, swollen channels, and changing visibility as the atmosphere lowers its stored water to the land in organized moving stripes. Within the warmer side of the cyclone, the atmosphere sometimes becomes less layered and more restless. Here the air is milder, often more humid, and capable of rising in a more vigorous way if the balance of temperature and wind allows it. This region is known as the warm sector, and under some conditions it becomes the part of the storm where thunderstorms develop. Not every bomb cyclone produces severe thunderstorms, and not every warm sector becomes unstable enough to support them. But when the ingredients align, this region can transform from a zone of strong wind and low cloud into one of towering convective clouds, abrupt rainfall, and rapidly changing local weather. The larger cyclone still governs the overall pattern, yet within this sector a smaller and more energetic form of motion begins to appear. The first ingredient is moisture. Warm sector air often arrives from lower latitudes or from regions that have recently passed over warm water. Because warmer air can hold more water vapor, it may contain a substantial reservoir of humidity in the lower atmosphere. This moisture does not by itself create thunderstorms, but it helps lower the level at which clouds can form and adds energy when rising air condenses. A humid, warm sector often feels heavy and soft near the ground. Even when the sky above remains layered or partly obscured, that feeling reflects an atmosphere storing latent energy, waiting for lift and instability to act upon it. The second ingredient is instability. Instability means that if a parcel of air is lifted, it becomes warmer than its surroundings and continues rising on its own. In practice, this usually requires warm and moist air near the surface and somewhat colder air above. The greater the temperature decrease with height, the easier it becomes for rising air to remain buoyant. In the warm sector of a deepening cyclone, upper-level cooling associated with a nearby trough can increase this contrast. Sunlight breaking through cloud cover can warm the surface further, though thunderstorms can also develop with little sunshine if the larger-scale lift is strong enough. The exact amount of instability is often uncertain until the event is close, because small changes in cloud cover, temperature, or moisture can alter the outcome significantly. Lift provides the trigger. In the warm sector, lifting may occur along the advancing cold front, along prefrontal troughs, near dry intrusions, or within zones where low-level winds converge. A prefrontal trough is a region of lower pressure and wind shift that develops ahead of the main cold front. It can organize rising motion before the boundary itself arrives. When air is forced upward in one of these zones and the atmosphere is unstable enough, cumulus clouds can grow rapidly into towering thunderstorm clouds. Their tops rise far above the layered cloud deck of the broader cyclone, marking a shift from steady ascent to deep convection, a form of vertical motion that is stronger, faster, and more concentrated. Wind shear is the fourth ingredient, and in the environment of a bomb cyclone it is often abundant. Wind shear means a change in wind speed or direction with height. Strong shear can help thunderstorms become more organized by separating the rising current from the descending rain-cooled air. Instead of collapsing quickly under their own precipitation, the storms can persist longer and take on more structured forms. Lines of thunderstorms may develop ahead of the cold front. Isolated rotating storms are also possible if the turning of the wind with height is pronounced and the local instability is sufficient. Still, strong shear alone is not enough. Without adequate warmth and moisture near the ground, the storms may remain shallow or fail to form. When thunderstorms do develop in the warm sector, They alter the atmosphere on a local scale. Rainfall becomes more intense and less uniform than in the broader stratiform rain bands. Lightning appears as electrical discharge within and between clouds or between cloud and ground. Thunder follows as the sound produced by the rapid expansion of heated air. Gusty downdrafts can spread outward beneath the storms as cooled air descends and reaches the surface. Hail may form if strong updrafts carry water droplets high enough into sub-freezing layers repeatedly, allowing them to grow in shells of ice. In some cases, especially where low-level wind shear is strong and surface boundaries are present, tornadoes may develop. These remain among the more uncertain outcomes and depend on details that are often resolved only shortly before the storms form. The warm sector can feel unstable even before storms appear. Low clouds may race northward. Surface winds may strengthen from the south or southeast. Temperatures may rise despite the broader storm system, and the air may become noticeably more humid. Pressure often continues falling as the cyclone approaches. These signals do not guarantee deep convection, but they mark a region where the atmosphere is becoming increasingly responsive to lifting, if the cap, a layer of warmer air aloft that suppresses convection, remains in place. The warm sector may stay cloudy and windy without many storms. If that cap weakens or breaks, thunderstorms can erupt quickly and organize along preferred lines. This region often contains some of the sharpest forecast challenges. Meteorologists may identify the warm sector and the presence of strong shear several days in advance, yet the exact extent of instability is frequently harder to determine. A broad deck of cloud can limit daytime warming. Slightly drier air at low levels can reduce buoyancy. A warm front positioned a modest distance farther north or south can change which communities enter the more unstable air. Because of this, forecasts for severe thunderstorms are usually expressed in terms of risk zones and probabilities rather than certainties. The large-scale storm may be well understood, while the most intense convective outcomes remain conditional. In the context of a 2-week weather shift, the thunderstorm sector represents the storm's most vertically energetic warm region. It is still part of the larger cyclone and still governed by its pressure field, fronts, and wind shear. Yet within this sector, the motion becomes more abrupt and locally intense. Air rises not only broadly but explosively in narrow towers. Rain falls not only steadily but in bursts. Wind arrives not only as persistent gradient flow but as sudden convective gusts. The calm logic of the larger storm remains present, but it is temporarily expressed through sharper and more forceful local events. Here the cyclone reveals a different face, one rooted in the same physics of contrast and motion, yet concentrated into storms within the storm. Warm, humid air gathers near the ground. Colder air aloft and strong winds above create an environment where upward motion can accelerate dramatically. The warm sector becomes a place of conditional energy, of layered instability, of clouds that may remain low and grey or may rise into towering forms depending on the precise balance of heat, moisture, lift, and shear. In this region, the larger bomb cyclone does not lose its identity. It simply concentrates part of its power into thunderstorms that occupy the warm side of its circulation. On the colder side of the cyclone, the storm enters a quieter but no less complex region. Here the air near the surface is cold enough, or nearly cold enough, for precipitation to take frozen or partly frozen forms. This is the snow and ice sector. It lies not in a single fixed place, but where the storm's moisture and lift overlap with a layered temperature structure that allows water to freeze, remain frozen, or melt and freeze again before reaching the ground. The same cyclone that brings rain and thunderstorms in its warmer regions can produce snow, sleet, or freezing rain here. The difference depends not simply on surface temperature, but on the vertical arrangement of the air from cloud to ground. Snow forms when ice crystals grow in clouds that are cold enough to support them. In the snow sector of a mid-latitude cyclone, rising moist air cools and condenses, then deposits water vapor directly onto ice nuclei, creating crystals. These crystals collide, branch, and sometimes join together into flakes as they descend. If the entire layer of air from cloud base to surface remains below freezing, the snow survives the fall and reaches the ground as snow. The character of that snow depends on temperature and moisture. Colder, drier conditions often produce lighter, finer snow. Slightly warmer and moister air can produce larger, wetter flakes that cling to surfaces and accumulate heavily on trees, roofs, and power lines. Yet the atmosphere is often more layered than a simple column of cold air. In many winter or shoulder season storms, a shallow cold layer rests near the ground while somewhat warmer air flows above it. This arrangement is especially common north of a warm front or near the wrapped sectors of a mature cyclone, where warm air is forced over denser cold air at the surface. In such a case, snow may begin high in the cloud, then fall into a layer warm enough to melt it into rain. What happens next depends on the depth and temperature of the cold air below. If the lower cold layer is deep enough, the drops can refreeze into ice pellets before reaching the ground. These pellets are called sleet. They bounce on impact and can accumulate in a dense, granular layer. If the cold layer near the surface is very shallow, the melted drops may remain liquid until they strike objects whose temperature is at or below freezing. Then they freeze on contact, forming glaze ice. This is freezing rain, one of the most hazardous forms of winter precipitation because it coats roads, branches, wires, and exposed surfaces with a clear and often heavy layer of ice. A storm does not need to produce a great depth of freezing rain to cause serious disruption. Even a thin coating can turn travel dangerous and add significant weight to trees and infrastructure. In this way, the snow and ice sector can become highly consequential even when total precipitation is not especially large. The position of this sector within the cyclone often changes as the storm evolves. At one stage, colder air may dominate north and west of the low, allowing snow to fall over a broad area. Later, warmer air may advance aloft and change part of that area to sleet or freezing rain. If the storm deepens and wraps colder air inward again, rain may change back to snow. These transitions are among the most delicate and difficult parts of forecasting. A shift of only a few degrees Celsius in a thin layer of air several hundred meters above the ground can determine whether a town wakes to wet snow, icy glaze, cold rain, or a mix of several types in sequence. The landscape shapes this region as well. Valleys can trap shallow cold air near the surface, making freezing rain more likely even when nearby higher ground experiences plain rain or snow. Mountains force air upward, cooling it and increasing snowfall on windward slopes, on leeward slopes. Descending air may warm enough to alter precipitation type. Open plains permit cold air to spread broadly and shallowly, sometimes allowing a large mixed precipitation zone to develop along coastlines. Marine influence may warm the lower atmosphere just enough to reduce snowfall near the shore, while inland areas remain frozen. These local adjustments are layered onto the broader storm structure, giving the snow and ice sector its fine regional detail. Wind continues to matter here. Strong wind can reduce visibility by blowing falling snow sideways and lifting newly fallen snow back into the air. Even light snow can become difficult to navigate if wind is persistent enough to create drifting and blowing snow. Wet snow, by contrast, may resist blowing but adhere strongly to branches and wires, especially when accompanied by gusts. Ice-coated limbs may fail under combined loading from precipitation and wind. Thus, the hazards of the snow and ice sector often arise from interaction. Frozen precipitation alone matters, but frozen precipitation combined with wind, terrain, and timing matters more. The temperature profile that creates this region is often maintained by the storm itself. Cold air is drawn around the backside of the cyclone and can wrap inward toward the center. At the same time, warm air may continue to rise over shallow surface cold air ahead of certain fronts. This means the storm is constantly redistributing the very layers that determine precipitation type. The snow and ice sector is not merely a passive area sitting in cold weather. It is an active thermal boundary zone, with air masses sliding over and under one another as the cyclone evolves. Observations indicate these layered transitions can shift quickly, especially near the margins of the freezing line, and it remains uncertain exactly where the sharpest changeovers will occur until the storm is close. Forecasting this region depends on frequent sampling of the atmosphere. Surface thermometers alone are not enough. Weather balloons, aircraft soundings, radar signatures, and model-derived vertical profiles all help reveal how temperature changes with height. Meteorologists look for warm noses aloft, shallow surface cold pools, and zones of intense lift that may cool layers through melting and evaporation. Even then, uncertainty remains because small model errors in temperature or timing can produce large differences in precipitation type. A county forecast may indicate snow in general, while the actual event includes a corridor of sleet or freezing rain where warm air intruded more strongly than expected. In the larger story of the cyclone, this sector is the cold mirror of the thunderstorm region. There, warm air rises rapidly and convectively. Here, cold layers govern the fate of falling water through quieter but equally precise thermodynamic rules. The clouds may appear dense and grey rather than towering. The motion may seem slower, the sound softer, the transformation more subtle. Yet the physics is exacting. Ice crystals form, melt, refreeze, or freeze on contact according to the layered temperature structure set by the storm. Through these processes, the cyclone deposits snow in fields and forests, sleet on roads and roofs, and glaze ice on branches and wires, translating atmospheric layering into the solid and slippery consequences of winter weather. Where the storm meets the coastline, the atmosphere begins to move the sea itself. This region lies at the boundary between air and water, where pressure, wind, waves, and shoreline shape come together to determine how coastal conditions change during a deepening cyclone. The ocean has already served as an outer source of heat and moisture, but here it responds more directly to the storm's force. Wind blowing over the surface transfers energy into the water. Pressure falling over the sea allows the water level to rise slightly. Long fetch, the uninterrupted distance over which the wind blows, gives waves time and space to grow. As the cyclone deepens and the wind field strengthens, the sea surface becomes rougher, higher, and more organized into moving swell and breaking surf. The coastline receives these changes according to its own shape, depth, and exposure. Waves begin as wind-driven ripples, but under sustained strong flow they grow into larger forms. The height of these waves depends on wind speed, duration, and fetch. In a broad and powerful wind field, the sea has time to respond fully. Waves lengthen, steepen, and travel outward from the strongest wind zone. Some remain local wind waves, still directly tied to the storm overhead. Others become swell, more regular wave trains that move away from their source and reach shorelines distant from the area of strongest wind. The sea therefore carries the storm's influence beyond the exact track of the low-pressure centre, extending danger to coasts that may never experience the strongest rain or inland wind. Low pressure contributes in a quieter way. When atmospheric pressure decreases, there is less weight pressing on the sea surface, and the water can rise slightly. This effect alone is modest, but when combined with strong onshore wind, it can add to storm surge. The abnormal rise of water above the usual tide level driven by weather. Surge depends strongly on coastal shape. Shallow continental shelves allow water to pile up more effectively than deep offshore zones. Bays, inlets, and estuaries can funnel the water inward, raising levels more than along an open straight coast. If the surge arrives near high tide, coastal flooding becomes more likely. The storm's impact on the shore is therefore not determined by the cyclone alone, but by the meeting of the cyclone with the geometry of the coast. On exposed shorelines, powerful surf becomes one of the earliest and most visible signs of the storm's marine influence. Waves break farther up beaches. Foam and spray are carried inland by gusts. Dunes and bluffs receive repeated impact from water that rises higher than under calmer conditions. Beaches may erode as sand is pulled seaward and redistributed along shore. Where protective natural features are low or already weakened, overwash can occur. With water and sand moving across barrier islands or coastal roads, along rocky coasts, the effect is less about erosion of loose sediment and more about force, spray, and direct wave impact against fixed surfaces. The direction of the wind matters greatly in this region. An onshore wind pushes water toward land and usually increases coastal risk. An offshore wind can lower nearshore water levels even while rough conditions remain farther out at sea. A wind blowing parallel to the shore may drive strong longshore currents that reshape beaches and complicate conditions for harbours and inlets. Small changes in storm track can therefore shift the coastal outcome substantially. If the low moves slightly closer to shore, one region may face stronger onshore flow, higher water, and larger surf. If it remains farther offshore, the same coast may experience strong waves but less serious flooding. Forecast uncertainty often narrows to these details near the time of impact. Harbours, estuaries, and tidal rivers respond according to their own internal shape. Narrow entrances can restrict flow, while broad shallow basins can amplify water level rise under sustained wind. In tidal rivers, the incoming surge can slow or oppose the river's seaward flow, increasing flood potential near the mouth and sometimes farther inland. Salt water may push into places normally dominated by fresh water. Floating debris, moored boats, docks, and waterfront infrastructure all respond differently depending on the combination of tide, surge, and wave action. Coastal flooding is therefore not only about water depth at the beach, it is about how the storm-driven sea enters and occupies the low spaces where land and water usually remain more clearly separated. Marine conditions beyond the shoreline become dangerous even before flooding begins on land. Strong winds create steep seas that challenge ships, fishing vessels, ferries, and smaller craft. Visibility may be reduced by rain, sea spray, or low cloud. The interval between waves can shorten in the strongest wind zones, producing chaotic water that is difficult to navigate safely. Even after the cyclone passes, residual swell can continue affecting the coast for some time. The sea does not calm the moment the sky begins to clear. Energy already transferred into the water continues to travel and break along the shore. Cold sector coastlines face additional complexity. If the air is cold enough, sea spray can freeze on exposed structures, creating marine icing. If snow falls near the shore, visibility and orientation can deteriorate further. In milder sectors, heavy rain and wave-driven flooding may occur together. Thus, the coastal region does not produce a single universal hazard. It produces a combination determined by storm track, wind direction, tide, coastal shape, and temperature. This combination may change over surprisingly short distances along the same shoreline. Forecasting this region requires more than atmospheric models alone. Ocean models, wave models, tide predictions, and coastal elevation data all contribute. Meteorologists and ocean forecasters estimate how strong the wind will be, how long it will blow over water, how the sea surface will respond, and how that response will interact with local shoreline geometry. Even then, uncertainty remains, especially in narrow inlets, estuaries, and low-lying developed coasts where small differences in water level can determine whether flooding reaches roads, homes, or remains confined to beaches and marshes. Observations from buoys, tide gauges, radar, and satellite altimetry help refine the picture as conditions develop. In this region, the storm extends its influence from air into water, and then from water back onto land. Wind roughens the sea, pressure lowers the burden above it, waves rise, travel, and break. Surge lifts water into places usually governed by tide alone. Beaches erode, harbours strain, coastal roads flood, and the shoreline becomes a moving boundary rather than a stable line. The cyclone, already understood as pressure, fronts, moisture, and temperature contrast, now reveals itself in the restless motion of the sea, where atmospheric force is translated into waves, elevated water, and the changing shape of the coast. After the storm has crossed oceans, upper air, pressure gradients, fronts, moisture pathways, temperature contrasts, wind fields, rain bands, thunderstorms, frozen precipitation, and the shoreline, it enters the most immediate region of all. Here the weather meets the built world and the daily habits of human life. Roads, rail lines, power lines, roofs, drainage systems, airports, farms, warehouses, schools, and hospital entrances all become part of the storm's final expression. The cyclone remains a physical system governed by air and water, yet in this region its meaning is measured through interruption. The question is no longer only how the atmosphere behaves, but how human structures and routines respond when exposed to prolonged wind, rainfall, cold, ice, snow, surf, and repeated shifts in temperature over many days. Cities respond first through their surfaces. Asphalt, concrete, glass, and steel do not absorb weather in the same way that soil, forest, or grassland do. Rain falls on streets and roofs, then runs quickly toward gutters and drains. If the rainfall is steady and the drainage network is clear, the city continues functioning with little visible strain. If rain bands persist or return repeatedly, water begins to collect in underpasses, low intersections, basement entrances, and older drainage systems not designed for the same intensity or duration. Urban flooding does not always require a river to overflow. It can emerge from the simple imbalance between how fast water falls and how fast the city can move it away. Wind in built environments behaves differently from wind over open ground. Buildings interrupt the flow, creating turbulence, sudden gusts around corners, and channeling through narrow streets. A steady regional wind can become erratic at pedestrian level, turning one block relatively calm and the next sharply exposed. High-rise structures experience stronger flow aloft, while cranes, scaffolding, signs, and temporary materials become vulnerable to repeated stress. Windows rattle. Loose objects travel. Tree limbs, especially after saturated soil or ice loading, may fall onto roads, parked vehicles, or electrical lines. The storm's broad wind field becomes fragmented by architecture, yet its force remains present in these local surges and vortices within the city. Power systems reveal another layer of vulnerability. Electricity networks depend on long connected lines, substations, transformers, and generation sources that must continue operating under strain. Wet snow adheres to lines and branches, ice adds weight. Strong gusts push trees into conductors or cause weakened limbs to fail. Floodwater threatens low equipment and access roads to critical facilities. In some regions, repeated storms over a 2-week period matter more than one intense event. The first system saturates the ground or weakens a branch. The second or third delivers the final gust or additional weight that brings failure. Outages therefore often reflect accumulation rather than a single moment of atmospheric maximum. Road travel becomes a direct measure of how the storm enters ordinary life. Rain reduces visibility and leaves standing water in low places. Strong wind affects high-profile vehicles, especially on open highways and bridges. Snow covers lane markings and changes tire grip. Sleet creates a surface that is granular and unstable. Freezing rain lays down clear ice that can be nearly invisible. Each of these conditions changes how quickly vehicles can move and how safely drivers can judge distance and braking. A road that remains technically open may still become functionally difficult if wind, water, darkness, and uncertainty combine. Transport systems are built for motion, yet storms remind them of the limits imposed by friction, traction, and sight. Air travel responds through a different set of sensitivities. Aircraft can often fly in conditions that inconvenience ground traffic, yet airports remain highly dependent on visibility, wind direction, runway condition, and the timing of arrivals and departures. A strong crosswind can limit operations on certain runways. Heavy rain reduces visibility and increases spacing requirements. Snow and ice demand de-icing, runway clearing, and careful sequencing. Thunderstorms near a terminal airspace can delay or reroute traffic far beyond the immediate storm center. Because the air network is interconnected, disruption in one region of the country can propagate elsewhere. A bomb cyclone affecting one corridor of the United States may therefore alter schedules in cities that experience little more than cloud or gusty wind. Railways, ports, and freight systems feel the storm through exposure and timing. Flooded crossings, downed trees, unstable slopes, rough seas, and wind restrictions can slow or interrupt the movement of goods. Agriculture responds in equally material ways. Excess rainfall delays fieldwork. Strong wind lodges crops, meaning it bends them over and reduces their ability to be harvested efficiently. Late snow or freezing rain harms early growth in some regions and fruit blossoms in others. Livestock require shelter from prolonged wet cold, wind, or heat swings. The storm's 2-week influence therefore enters the food system not only through dramatic damage, but through timing, delay, and the changed condition of land and plants. Homes experience the storm at the scale of roofs, doors, pipes, and daily habits. Residents close shutters, secure outdoor furniture, clear drains, check forecasts, and alter travel plans. Heating demand increases when colder air arrives, and wind removes warmth more efficiently from buildings. In warmer, wet sectors, humidity rises and ventilation changes. Pipes in exposed places face greater risk if temperatures fall low enough after rain or thaw. Roof leaks that remained minor in calm weather become significant under persistent rain and wind. The storm becomes part of domestic space through sound, drafts, flickering lights, and the repeated need to monitor the outside world. Public services operate under layered pressure in this region. Road crews pre-treat highways for ice where forecast confidence is high enough. Utility workers stage equipment and personnel for restoration. Emergency managers monitor flood-prone zones, coastal access points, shelters, and communication systems. Schools and workplaces adjust schedules or close temporarily when transport and safety become uncertain. Hospitals prepare for power interruptions and increased demand associated with injury, exposure, or delayed care. These responses are not separate from the weather. They are part of the human system that has evolved to absorb atmospheric disturbance while trying to preserve continuity. Yet uncertainty continues to shape every decision. A forecast may indicate strong wind over a broad region, but whether one county loses many trees or only a few depends on soil condition, species, pruning history, and the exact corridor of gusts. A rainfall outlook may suggest flooding risk, but the realized impact depends on storm drainage, recent rain, land cover, and the timing of the heaviest bands. A snow forecast may be broadly correct while the zone of freezing rain shifts by enough distance to change the nature of disruption entirely. Human systems must therefore prepare for ranges of outcome, not only for a single expected state. In this region, the cyclone reaches its innermost practical meaning. It becomes not just air in motion or water falling, but altered routine. Commutes lengthen or stop. Deliveries are delayed. Classrooms empty. Waterfront streets close. Utility crews work through the night. Families listen for changing forecasts and watch tree branches in the dark. The atmosphere has crossed every earlier region and now rests against the ordinary structures of life, testing how flexible they are, how connected they are, and how well they can absorb 2 weeks of shifting strain delivered by a deep and changing storm pattern. At the innermost layer of the story, the storm is no longer described by ocean, jet stream, fronts, wind, rain, snow, coast, or city alone. It becomes a matter of interpretation. This region is the forecast itself, where observation, physics, and uncertainty are brought together and translated into expectations about the days ahead. The atmosphere remains a continuous moving fluid, but human understanding of it arrives through models, probabilities, maps, advisories, and measured language. In a period described as a bomb cyclone warning and a weather change lasting roughly 2 weeks, the deepest question is not only what the storm is doing, but how confidently that behavior can be known across space and time. Forecasting begins with observation. The atmosphere is sampled by surface stations that record temperature, pressure, wind, and precipitation. Weather balloons rise through the air and measure how temperature, humidity, and wind change with height. Radar shows where precipitation is falling and how it moves. Satellites observe cloud patterns, moisture fields, surface temperatures over land and sea, and the broad structure of the atmosphere across regions where direct measurements are sparse. Aircraft add information along flight paths, and ocean buoys report marine conditions over waters where storms often intensify. Each observation is only a point or a narrow path, yet together they form the initial picture from which forecasts grow. That picture is then used to begin numerical weather prediction. In these systems, the atmosphere is represented by equations that describe motion, heat transfer, moisture changes, pressure, and the rotation of Earth. Powerful computers solve these equations repeatedly over a 3-dimensional grid, advancing the atmosphere forward in time. The result is not a single perfect answer, but a simulation of how the atmosphere may evolve if the starting description is accurate. and if the model represents the physical processes well enough. Since neither of those conditions is ever complete, every forecast carries uncertainty from the beginning. This uncertainty grows with time. Over the next day or two, the atmosphere's larger structures are often predicted with useful skill, especially when the pattern is broad and well observed. Beyond that, small differences in the initial state begin to matter more. A slight change in the position of an upper trough, the strength of a temperature gradient, or the speed of a surface low can alter where the heaviest rain falls, where freezing rain develops, or how close the strongest coastal wind comes to shore. Over a 2-week period, these differences become even more important. The broad pattern may still be recognized, but local details become less certain. This is why long-range outlooks are usually expressed in terms of above normal or below normal temperatures, or wetter than average or drier than average conditions, rather than precise local forecasts for each day. A probability outlook does not mean that forecasters are unsure whether weather will occur. Weather always occurs. It means that the future atmosphere can unfold in more than one plausible way, and the forecast is describing how likely certain outcomes are relative to average conditions. If an outlook indicates an increased chance of wetter than normal conditions over a region, it does not promise rain every day or equal rainfall in every town. It means that, based on the model guidance and current atmospheric state, the odds favour a period that is wetter than what is typical for that time of year. The same is true for temperature. Above normal warmth does not exclude a cool morning, and below normal conditions do not require constant cold. These are statements about the overall tendency of the pattern. Ensemble forecasting helps clarify this region. Instead of running one model forecast alone, meteorologists run many forecasts with slightly varied initial conditions or model formulations. Each forecast in the ensemble is physically plausible. When many of them cluster around a similar solution, confidence increases that the larger pattern is being captured well. When they diverge widely, confidence falls. The value of the ensemble is not that it removes uncertainty, but that it measures it more honestly. A bomb cyclone signal that appears in many ensemble members carries more confidence than one that appears only in a few. A 2-week period of active storminess is more believable when multiple simulations maintain a similar trough ridge arrangement across the continent. The public often encounters weather through headlines, icons, and simplified labels. These are useful for attention, but they compress complexity. The phrase bomb cyclone describes a rapid deepening, yet it does not specify where the strongest wind will be, whether the rain will train, how far inland the warm front will reach, or which valley will hold freezing air longest. Similarly, a national map shaded toward colder or warmer probabilities cannot reveal the exact feel of each town on each day. The forecast region is therefore a place where language must balance clarity and restraint. It must name the broad risk without pretending to know every local detail too early. Uncertainty in forecasting is not a flaw added to an otherwise perfect science. It is part of the atmosphere itself. The atmosphere is a chaotic system, meaning that very small differences can grow over time. This does not make forecasting impossible. It makes forecasting conditional. The broad pattern can often be understood with considerable skill, especially when strong large-scale structures dominate the flow, but the exact timing and placement of the most intense impacts remain partly open until the event approaches. This is why forecasts are updated repeatedly. New observations enter the models, the ensemble spread changes, radar reveals what is actually developing. Advisories narrow from broad pattern language toward more local warnings as confidence improves. In the context of this storm period, The most reliable guidance often lies in the structure of the pattern itself. A persistent upper trough, repeated low-pressure development, a corridor of moisture transport, and continuing temperature contrasts can support confidence that the nation will experience unsettled and shifting weather across many days. The exact count of storms, the peak intensity of each, and the precise placement of hazardous boundaries remain less fixed. Forecast confidence is therefore layered, much like the storm itself. High confidence may exist in the continental trend, moderate confidence in the regional outcomes, and lower confidence in the street-level details far in advance. This final region brings the narrative inward to the limit of what can be known before weather becomes observation. Beyond this point, there is no deeper hidden chamber inside the storm, only the meeting of forecast and reality. Maps are revised, probabilities rise or fall. A coastal flood forecast shifts upward by a small but important amount. A freezing line moves northward by a few counties. A rain band stalls longer than expected. A city prepares for strong wind and receives mostly steady rain, while another on the edge of the guidance experiences damaging gusts. The forecast remains an act of measured understanding, always improving as the storm draws closer, never entirely free from uncertainty. In this innermost layer, the bomb cyclone warning and the 2-week weather change are understood not as fixed promises, but as evolving judgments built from science, observation, and humility. The atmosphere offers patterns, not guarantees. Meteorology studies those patterns with increasing precision, yet it preserves caution where caution is warranted. Here the storm becomes knowledge in progress, a careful reading of air, water, and motion translated into human expectation. It is the quiet final region of the whole system, where the deepest truth is that the weather can be known broadly, refined steadily, and never held with absolute certainty before it arrives. The storm gradually leaves behind the language of warning and returns to the quieter language of aftermath. Pressure rises in some places and falls again in others as the pattern continues its long movement across the continent. Rainwater drains from roads into soil, creeks, and rivers. Snow settles into a more even surface after the wind weakens. Ice begins to soften where the air warms and to harden where cold remains. Along the coast, the waves take longer to calm than the sky, and the sea continues carrying the memory of the wind after the strongest gusts have passed. Across the United States, the atmosphere keeps adjusting itself. Warm air and cold air do not stop meeting. Moisture does not stop moving. The jet stream continues its high, curving path above the land and ocean. The deep cyclone that seemed at first like a single event is revealed, in the end, as part of a much larger circulation that never truly rests. One storm deepens, matures, and weakens, while the broader pattern still guides what may follow behind it. Some regions clear, others remain under cloud, some begin drying, others continue receiving rain or mountain snow. The change is not sudden. It eases from intensity into persistence, and from persistence into ordinary variability. In this quieter view, the weather becomes less a dramatic object and more a steady natural process. Air flows, cools, warms, rises, sinks, and carries water through invisible paths above the ground. Forecasts improve, then yield to observation. The maps that once showed uncertainty are replaced by damp fields, bright snow, bent branches, drained gutters, and slowly returning routine. The storm has moved through outer ocean, upper sky, boundary, cloud, coast, and city. And now it becomes part of memory and record. What remains is not only disruption, but understanding. The atmosphere changes because contrast exists, because Earth turns, because water and land respond differently to heat, and because the planet is always redistributing energy from one place to another. In that constant motion, even a bomb cyclone is only one passing shape in a much larger and calmer whole.